Good evening. Welcome to Lecture 3 of Unit 2 of Topic 3, Resistance. This video is going to be covering the main ideas of Chapter 8.1 and 8.2 of Book 1, and you should do that reading before class. Here are your learning intentions and success criteria for this chapter. Please pause the video and attempt to complete the KS table there down on the right. Okay, so having a look here, we've got 3 success criteria. We're looking at defining resistance, calculating using Ohm's law, and comparing ohmic and non-ohmic resistors. And there's also a reference to using experimental data up here in our learning intention. So our knowledge really should be asking us, well, what is resistance? If we don't know what it is, we can't define it. If we're going to use something called Ohm's law, we need to know what it is. And if we're going to compare these, this is very much a high level knowledge based cognitive verb. Well, we're going to need to be able to know what these two things are. In terms of doing, calculate means we need to work with it. However, we also need to know, well, how do we use it for experimental data, so using it in a very specific circumstance there. So there's a lot of things coming out of this topic, even though it's quite short. So let's start with circuits. Here's a circuit. Okay, you can see that the switch on it's been closed, and the animation will probably loop in a second. Okay, and we can see the electrons moving around through it. There, remember, the battery here has a potential difference on it, and so it creates an electric field through the current, through the wire, and that causes a current to travel. And this current is a reflection of, well, how much charge, how many electrons pass a point per second. Well, why do they move at this speed? Why not faster? Why not slower? And the answer is resistance. Now, while electrons are very small, and there is a significant amount of space between atoms, there's still a lot of chances for electrons to collide into atoms as they travel through a material. And so this is an animation, hopefully we can see it okay, where you can see the little blue dots. These are the electrons travelling around, and if you just sort of relax your eyes a bit, in general they're moving from left to right. However, there is the occasional electron here that is drifting backwards. Like there's one right here, just slowly moving backwards until the animation resets. And so there's one that's just sort of hanging around, not doing much. Okay, so while the whole thing on general is moving left to right, some of them are moving backwards, some will just drift around aimlessly until something else gives a bit of a collision, because there are other physical things at play. Okay? Now when the electron collides, it loses energy, slows down, reduces the current, and that lost energy becomes heat energy. And when you make something hotter, the resistance continues to increase, which then will continue to make it hotter. So you can see it's sort of self-perpetuating there. Now, with resistance, there is a formula that talks about the physical properties of a material and how it will make the resistance of that material. This might be a good topic for a student experiment. Now, the first bit is straightforward. It's length. If the length of a piece of wire increases, the resistance increases. So they are proportional to each other. The second one is cross-sectional area, or how thick the wire is. And what I mean by that is comparing, say, a wire of this thickness to a wire of this thickness. Okay, the second one is a lot thicker, and yes, there would be more atoms in here compared to in here, but the density of atoms is not any greater, but that means there's still more space for electrons to go through, and so resistance is inversely proportional to area. Okay, while area increases, radius squared, some of the things end up getting cancelled off, and so it's just proportional to area. Finally, with these two factors, there is a constant of proportionality. Okay, and we give that the symbol rho. This is this weird looking P. Okay, that we draw it. And I'll show you how I would write this. Just up and around, rather than doing the whole down and sort of around. That's a very childish looking P, that you would probably do based off your English classes. Okay, so rho is the constant of proportionality. It's the resistivity, the electrical resistivity of a material. It's pretty similar to how every material has a specific heat capacity that we learnt about in our previous topic. And so this makes the equation R for resistance equals rho times L divided by A for area. Now note, this is not an examinable equation. It will not appear on your formula booklet, so it can't appear on your final exam. The text does have a couple of questions on it that I'll get you to practice for just skill development with your algebra, but it is a pretty decent topic for student experiment if you want to look at resistivity of different metal wires. Alright, for a quick activity, I'd like you to draw a diagram or two to help you visualize those three physical properties that determine the resistance of a wire. So using that formula, okay, I want you to draw 1 to 2 diagrams that help you visualize that explanation I've just given you. And you can find lots of pictures like this online, so feel free to go searching for inspiration. Great, hopefully you've done that. So let's continue on. In the 1800s, a physicist by the name of Ohm did some testing on electrical conduction and found that voltage and current are proportional to each other. If, and only if, he kept the other parts of his circuits the same. That means he had to use the same length, the same area, and most importantly, the same temperature, because length and area, yeah, if you heat up a material, it gets slightly bigger, but small lengths, it's not going to be a significant amount, but temperature's kind of a big deal. It will change. Now, while Ohm didn't do it, he did get the naming rights for it, and that's why we measure resistance in ohms. They found that by using that resistivity formula, that the proportionality between voltage and current was equal to the resistance of the wire, and we came up with Ohm's law. I equals V divided by R. Now, a little small issue. While this is sort of the logical way of thinking about it, the current is the result of the voltage, how hard we push on the electrons, divided by the resistance. A lot of texts don't write it like that. They write it like this one here on the left, V equals IR. Personally, I think this is just because it fits on one line, so it's easier to write with a typewriter, similar to how Newton's second law is F equals ma, even though the force is not the result, the force is the cause. And I think it's written this way because IR is alphabetical. For some ineffable reason, I don't know why, the formula booklet has it as this, R equals V divided by I, and this is not too bad when it comes to defining resistance. So you can use it there as a memory jog that this is the definition of resistance. However, it is still a little bit weird, in my opinion, for it to be written like that, because these two things do not cause the resistance. The resistance is the connection between the two. But regardless of which of the three ways it's written, all three are Ohm's law, and so you should be able to use them in any way you wish, or any way that you're asked. Now, so let's do an example. We have here, determine the resistance of a car horn if 1.5 ampere flows when 12 volts is applied to it. So let's use that last definition we have it. We had that R is our unknown. We have that the current equals 1.50 amps, and we have that the voltage equals 12 volts. Okay. Now, if regardless of which one you start with, let's go with I equals V over R. We can substitute those in and rearrange. R would be multiplied over V equals IR, and then I would be divided back. R equals V over I. So R would equal 12 divided by 1.5, which should be equal to 8 ohms. Now the symbol for resistance is this weird looking omega thing, like a circle with two doors opened up underneath. Okay, and this is the symbol omega, sometimes pronounced omega, and this was part A. Okay, so we've got part B. Determine the voltage across the same car horn when 250 milliamps is flowing. Okay, well in this case we're assuming here the resistance is the same because we're going to use the resistance from the previous part to work out the voltage now. So let's write our formula. V equals IR. We know that I is 250 milliamps. 250 times 10 to the negative 3 times 8. And that would work out as being, let's see, 4 times 250 times 10 to the negative 3 would be 1 volt, so that should be 2 volts. And we have an answer of 2 volts. So with questions like this, there's only 3 things you can work with. You find 2, sometimes you might have to assume one of those things if it comes from something else. Okay. So, having examined physical properties and how the discovery was arisen at in terms of the equation, we have a definition for resistance. So resistance is the physical property of a material that inhibits or slows down electrical current, and we find it by taking the ratio of voltage to current. Okay. So let's think about how this would apply to things that we use in day-to-day life. When a substance, like a piece of wire, obeys that formula, it's called an ohmic device. Now, simple materials, nichrome wire, a length of copper wire, all these things would be good ohmic conductors. Okay? As long as they don't get too hot and as long as you don't apply too much voltage on it. However, objects like light bulbs, diodes, and most electrical circuit things are non-ohmic, and that's because the ohmic resistor requires temperature to be constant. You can mimic an ohmic resistor with a light bulb if you don't leave the light on for very long when you take a measurement. So if you flick it on, take the measurement, flick it off. However, if you leave it on for a while, it starts to heat up, and so then the resistance is changing. Okay. Remember, if you make the voltage too high, then this law no longer applies. Now, the biggest difference between these two and how you can recognize them is using a graph. An ohmic resistor will look like this. It'll have a nice, straight, linear relationship between voltage and current. It doesn't matter what's on the x or the y axis. All that'll do is change the gradient. And like we'll practice in class with our experiment, we can work out the gradient regardless of which is on the axis. You just need to pay attention to which is on the axis. Okay? A non-ohmic resistor in comparison might look a bit more like this. So you can see here we've got this first jump up, then as the object starts to warm up, it starts to curve off a little bit there. And we could graph that, and as we've seen with our data analysis, curves like this generally means proportional to the square root, and so we could go and test that and see if we can linearize our data. Okay, so in this video we've covered the following. We have looked at the physical properties of resistance, we've established Ohm's law and done some practice with it, and we've looked at the difference between an ohmic and a non-ohmic resistor. Now, for your entrance slip to class, I'd like you to complete questions 1 to 5 in chapter 8.1 and 1 to 4 in chapter 8.2. Check your learning PDFs. Copy your answers for these into the 3.2.3 space on eLearn. Thanks very much for listening, guys. Have a great night.